because say you have your signal source like this, V and RS. Sorry. So with one port nonlinear element, the amplified signal is available across that nonlinear device itself. But that's not what you want, right? Let's say I'm speaking, I want to amplify my audio signal using an amplifier. Let's say you go to a Coldplay concert without getting caught in camera, and then there you see a lot of audio amplifiers. So they have to basically amplify the signal and provide it at a speaker. So which means I should be able to basically amplify the signal and provide it across a load resistor. For example, a speaker is a resistor with resistance of 10 ohms, 20 ohms or something. So which means I cannot have a one port device. How many ports I should have? 2 ports. So I already told that I should have 2 terminals to make a port. So what is the minimum number of terminals I need to make a 2 port? 4, or I asked minimum. 3 is sufficient because I can have one common port. Sorry, one common terminal. Let's say terminal 1, terminal 2, and this can be common too. Make sense? So in practice, this is what you want to do: get a 2-port amplifier. And if I mark the terminal voltages, this is the convention. Current entering the port is I1. Similarly, current entering the port here is I2, and the voltage is V2. So from your experience, tell me if this should behave like an amplifier. Should this be a linear 2-port network or a non-linear 2-port network? It has to be a non-linear 2-port network. That much is clear. Now our question is, how should the characteristics of this non-linear 2-port network be so that it behaves like an amplifier? Okay. For example, when we had a 1-port non-linear network, we saw that it has to have a negative slope so that we get amplification. Similarly, let's try to understand what should be the conditions on the nonlinear characteristics of the 2-port device so that we get amplification. Okay, so if I were to write this, I want to understand what nonlinearity I should have so that I get amplification. This is my goal. But before that, let's understand how to characterize a 2-port network. Now for a 1-port network, where is it? Yeah. For a 1-port network, it was simple. I had only one voltage and one current. I just had to specify the relation between that current and that voltage. Whereas for 2-port network, how many currents I have? I have 2 currents. So how many equations I should have? 2 equations for 2 currents. And each of the current can depend on both voltages. Is that okay? So this is just a general point here. I'm just making it. So basically I should have I1, some nonlinear function of both voltages V1, V2. Similarly, the other current I2 is some other nonlinear function of, fine, nothing complicated. Now if this were a linear 2-port network, let me just mark it. This is for nonlinear network, right? If this were a linear 2-port network, the current will be related to the voltages in a linear fashion or a non-linear fashion. So essentially, if this was linear, I will have the current to be some constant times V1 plus some other constant times V2. Similarly, I2 will be some other constant times V1 plus some other constant times V2. And what are those constants called? Turns out they are called Y parameters. So just like filling a matrix, you write it Y11, 12 for the first row, 21 and 22 for the second row. So this is the characterization for a linear 2-port network. I have not done anything really extraordinary. I know that this is for nonlinear. For linear, I know this should be a linear relation. It's a linear combination of V1, V2, and the jargon is this constant is called Y11, Y12, and so on. That's just your typical matrix, representation. Okay, but this is just a side. But our goal is to understand what should be the nonlinear characteristics of this two-port network, so that it can give me amplification. So, which means now I know this has to be a nonlinear network, and nonlinearity alone is not sufficient. What should I give? Some DC source. So, let us say I have a DC source somewhere. I'm just drawing it for the sake of it, representation. So, which means if I look all the voltages, if I look at V1, V1 will have an operating point voltage. I'll call it V1O plus the small signal voltage delta V1. Fine. Because now in my circuit I have both a DC part as well as a small signal that I want to amplify. Is that okay? Similarly, if I write for V2, that will also have an operating point voltage. I'll call it V2O plus delta V2. Fine. Is okay? Huh? Oh, sorry, VB. Sorry, should have been VB. This is some other voltage VB. Okay. Yeah, thanks. So, which means even if I look at the currents, they will also contain an operating point current and a small signal current. So, if I were to write it, it will be I1 0 plus delta I1. Okay. That will be a nonlinear function of V1, V2, where V1, V2 are these. Okay. So, if I write it, it becomes apparent. So, this is essentially F1 of V1 plus delta V1 I mean the same relation. I am saying that now I have an operating point current and a small signal current, operating point voltage and a small signal voltage. So, of course, if for I1 you have this, I2 also you have the same. So, this I will just write it for the sake of completion. It's not crucial here. So, again, remember my goal is to see if I get amplification here, right? So, which means let's first try to find out what is the small signal amplification we get. In other words, let's at a top level, let's try to solve for the circuit for small signals. So, we'll solve for the circuit, find what is the small signal gain, and based on that we can make conclusions on the nonlinear functions F1, F2. Is okay? That's what we are trying to do now. Now again, remember I have a nonlinear function. Once again, I'll assume that my delta V's are sufficiently small. How small we'll see later. But let's assume that they are sufficiently small to make small signal approximation. So just like for the one-port nonlinear function, we expanded using Taylor series. Here also I can expand using a two-variable Taylor series. So I'll just write it. If you don't remember, it's okay. So this is how it will look like. So the steps is not important, the final result is important. So this is going to be this is V1O, V2O. I made a mistake, this should be V1 operating point plus delta V1. If I expand this, I'll have F1 of V1O, V2O. Plus now I'll have partial derivatives, or I'll say, F1 by dou V1 times, and this should be evaluated at the operating point times delta V1. Similarly, I have partial derivatives of V2 at the operating point times delta V2. You will have delta V1 square, delta V2 square, that we'll ignore. That's a small signal approximation. So, which means now, this is again I1 operating point. So, this is my operating point current, which is same as this. So, this cancels out. And basically cancelling out the operating point terms. Okay. So, we end up with this, and this is what you should understand. So, now I have delta I1 as some partial derivative, that is some constant, times delta V1 plus partial derivative of with respect to V2, which is some other constant, times delta V2. Similarly, I can write for I2 as well. So, I will use small variables. Delta I2 I'll have the same thing, only the nonlinear function changes from f1 to f2. So once again, what we have done is essentially take this nonlinear two-port network. For small signals, we have essentially linearized them, because now I see my delta I1 is a linear combination of delta V1 and delta V2. Because these are all slopes, right? Just like the one port thing, these are all partial derivatives evaluated at the operating point. That is going to be some number, a constant time delta V1, another constant times delta V2.
Sir, we have expanded using
Correct.
series.
Yes.
Sir, so that equation you can explain once again. Means delta V1 upon delta V2.
Oh, I mean this is the expansion.
Sir, can you tell me exactly that term delta V1 upon delta V2?
Oh, this is the partial derivative. You remember partial derivatives, right?
Yes.
It's a nonlinear. It's a function of two variables. I'm taking the. I mean, this is how the Taylor series works. Okay. I mean, you should ask Taylor. Right? See, it's a partial derivative of this function with respect to V1. I have two variables, V1, V2.
Oh,
You take the partial derivative at the operating point. That's all.
yes.
So now you see that this basically equation here resembles something like this. Expected, because now we have linearized the network. So if I were to give it names, so this will be my Y11, small signal Y12. This is Y21. Is that okay? Just giving it some names, that's all. Nothing major. Huh? Sorry? Correct. Y11 is essentially partial derivative of the function f1 with respect to v1, and you have to evaluate this at the operating point. For a one-port network, you didn't have any confusions. You just had one slope because you had one voltage, one current. You find the slope of the nonlinear characteristic at that operating point. Here you have two variables, so you have to do partial derivatives. So now at least mathematically we know how to model this. Let me erase this. So now let's try to draw the small signal equivalent circuit for this MC. So this is the equations that are of interest to us. Now I'm trying to draw the small signal equivalent for this based on the equations here. So for small signals, what do you do for the DC sources? You make them zero. Voltage source is zero, current source is zero, right? For voltage source, it's a short circuit. If it's a current source, if you make the current to be zero, open circuit. So here, let's say I short this. Done. So which means maybe I'll redraw it here separately. I have only V in. I have RS. Now I have the port current delta I1 entering. I'll call this delta V1. Similarly, at the other end, I have RL. So this is delta I2, delta V2. So now this nonlinear two-port network, we know for small signals behaves according to these equations. Now I'm trying to draw an equivalent circuit based on the equations. If you were to rewind back for one-port network, that nonlinear characteristic, when I linearized it, it effectively became a resistor. Correct? Similarly, we are trying to find what is the linear circuit for this nonlinear two-port network. So let's use the equations and write. So first let's see this one. I say delta I1 is sum of two currents. Correct? So I should have two paths. Let's look at the first term. It is saying, sorry, this is Y11. It is Y11 times delta V1. So the current is the voltage times a constant. How do you model it? It's a resistor. What is the value of the resistor? Yeah, I'll say its conductance is Y11. Okay. So that is the first term in the current. Second term it says, I'm sorry, this should have only the partial derivative is Y12. Y12 times delta V2. That should be this current. Now what this means, I am sensing delta V2 and pushing in a current in this branch. How do I model this with circuits? I need to have a current source of this value, but the value of the current source depends on what quantity? Y12 is a constant, so it depends on, it's a current source whose current value depends on another voltage delta V2. How do you model that? It's a dependent source, voltage controlled current source. So I'll say its values Y12 times delta V2. It's okay. This basically models the first equation. Now similarly, let's do at the output side. I have delta I2. Delta I2 is sum of two currents. Let me write it clearly. This is Y21. I have two currents. So first let me make two paths for the currents. Okay. Let's look at the first path. It is Y21 times delta V1. So the current, let us say in this branch, should be a constant times delta V1, and delta V1 is here. So we have to sense this delta V1 and push in a current dependent on that. What do you do to model? Another dependent current source. So it is basically Y21 times delta V1. This is the first term. Second term is essentially delta V2 times a constant. Delta V2 is this voltage. I need to have a current here which is dependent on this voltage. What is the way to model? A resistor. So this is how the nonlinear two-port network will look like for small signals. Again, how small it is we have not seen, but let's assume that we'll find out the condition later. Okay, so now of course, let me write this clearly. Now basically again our goal is the following. I want to find what should be the nonlinear characteristic. I can find the small signal gain from the input to the output. I can solve for this circuit, linear circuit. I'll get an expression for the gain, and the gain will depend on all the Y parameters. I want to have a very large gain. So from the equation you can find what should be the condition on Y parameters. Once I know what should be the condition on Y parameters, I know how should the nonlinear characteristic look like. Right? Now of course you have to solve it, but I usually say my life is too short for me to solve algebra in class, but you guys have much longer life, you solve it later. So instead of solving it, I'll give you a qualitative approach. Let's just see this and wrap up today. See, I'm just taking this circuit. So now tell me, let's look at this term. So what is this current source saying? It is saying how much of the output voltage is impacting the input side. If you want to have an amplifier, you want to have conduction from the input to the output or output to the input. So if you want to have a good amplifier, what should be the ideal value of this? Should this be present or not present? Should not be present. If this should not be present, what should be the Y parameter condition? This term should be 0. Is this clear? I am merely saying that for a good amplifier, you should have only conduction this side. Whereas this current source is saying how much of the output is impacting the input. I don't want that ideally. So that straight away gives me Y12 to be 0. So I'll erase this. Now let's look at Y11. So what's happening? The input voltage is getting divided between RS and Y11. That is what is delta V1. This delta V1 is what is impacting the second port. So for a good amplifier, if you want to have a large gain, how should the resistance value be? It should be ideal value. It should be high. Ideally it should be, if resistance is infinity, this is the conductance. What should that be? Remember, Y11 is a conductance, 1 by resistance. Similarly, let's look at y21. So I'll remove y11 then. I look at y21. What is y21 saying? I have the input that produces a delta V1. I am pumping in a current dependent on that voltage. If I want to have a large gain, how should y21 be then? Infinite or very large, right? This is clear because y21 is saying how much of this voltage is getting converted to the current. So this should be essentially very large. And what is y22? What is y22 doing? I have some current generated. That current, some of the current is getting stolen by y22. Only remaining current flows through my load. Ideally, how much of the current you want to flow through the load? All of the current. So what do you want y22 to be? The resistance should be infinity. Y22 should be? So this is the ideal Y parameters for a good amplifier. Okay. So now it's pretty simple. Let's just look at the characteristics and wrap up, right? See, let me erase this. Now once again, remember, I'll take only these two. Y21 is essentially partial derivative with respect to V1. Y22 is partial derivative with respect to V2. And if I were to jog your memory, I had I1 as F1 of V1 comma V2, I2 as F2 of V1 comma V2, right? So what I am saying now is, I know this information about the small signal Y parameters, which means I know how the partial derivative should look like, correct? So which means, let me make some space here. If I try to sketch I2 versus V1 for, let's say, different values of, I2 versus V2 for different values of V1. The relation between I2 and V1 is given by Y21. Sorry, I'm looking at I2 versus V2. The relation between I2 and V2 is given by Y22. And ideally, what do you want y22 to be? So which means if I sketch the characteristic between I2 and V2, the slope should be 0. If the slope should be 0, the actual characteristic, how should it look like? Parallel to x-axis. So basically, it should probably look like this for different values of even I'm drawing. This is how it should behave for small signals, so that the slope is 0. That's what we are saying, y22 0. Now from your understanding on passivity, tell me how should the characteristic look like now? This is only for small voltages, right? For small signals the slope is 0. But if I were to sketch the full characteristic, can it keep doing this? What should happen now? It should come to what point? So it should basically come like this. Correct? Now similarly, if I do the same experiment for y21, that is I plot I2 versus V1 for different values of V2. My y21 should be very large. The slope should be very large. How should the characteristic look like? Should be parallel to the y-axis. So let's say it might look something like this. Again, this is for small signals, right? For small signals, it is parallel. If I try to sketch the full characteristics, how should it look like? It should again come to origin like this. Now, I'm sure you have seen some device which has characteristics like this. What is it? MOSFET. And that's exactly why you use MOSFET. And for MOSFET, it turns out the gate current I1 is always 0. So these conditions are automatically satisfied. So I just want to end with this thought that any nonlinear 3-terminal element which has small signal Y parameters like this can be used as an amplifier. And it turns out all transistors satisfy this condition for Y parameters. For a MOSFET, it turns out Y11 is 0, this is 0, this is large and this is 0. If you take a bipolar junction transistor, you have similar Y parameters, just that Y11 might not be exactly 0, might be a very small number. But that said, any transistor you will have, MOSFET, FinFET or whatever FET you will have in the future, for small signals around some operating point will satisfy this condition for Y parameters. And in this course, we will focus only on MOSFET, and we will start with MOSFET. We'll start looking at it from next class.